Hello, everyone. Okay, so I will start by introducing myself. I'm Franco Terranova. I'm a PhD student based at the RIA Center of the Université de Lorraine. I'm currently in the RESIST team. We work on many projects on resilience of networks, and I'm currently at the second year of my PhD. And my PhD project focuses on using AI solutions, and in particular reinforcement learning, for who's aware of that, to create a model that is able to find critical vulnerability paths inside networks. We're going to see this use case today, together with a more general concept of AI and vulnerabilities. So the name of this speech is, Can AI help us understand vulnerabilities? We're going to start by a simple definition of vulnerability, see how they are disclosed, focus specifically on language models, and then we're going to see some use cases. So starting by one possible definition of vulnerability, a vulnerability is a weakness in a system, software, hardware, or process that can be exploited by an attacker to gain unauthorized access, disrupt operations, or compromise data integrity. This is one of the thousands of possible definitions. What we have to mainly take out from this is that vulnerabilities are weaknesses, and we can find them on many levels. They can be at the software level, they can be at the hardware level, also at the human level, configuration level, process level. And one question that may arise is, how do we find these vulnerabilities? So according to the common vulnerabilities and exposures standard, we have a reporting pipeline that consists of the following. We have at the beginning a vulnerability researcher or a white hat hacker that discovered the vulnerability, and the report pipeline will then start. We have a phase of triage where the vulnerability, if it's a known issue, will be not reported. Subsequently, a CVE ID will be requested. This will be a unique identifier that characterizes and identifies the vulnerability, and it will be reserved. However, before being published, the user that discovered the vulnerability should submit some details, and these details will be fully analyzed to understand if the vulnerability is an issue or not an issue. And if it's an issue, the vulnerability will be published and the CVE ID will be finally allocated. So once published, these vulnerabilities can be found in many databases. One of these is the National Vulnerability Database. This is a database of the National Institute of Standards and Technologies. And here we can see an example of a vulnerability that we can find. So as you can see, we have the CVE ID. The CVE ID is composed by a specific structure. We have the year of publish, and we have a unique identifier after that identifies the vulnerability within the year of publish. Subsequently, you can find a description of the vulnerability. This is a free format textual representation that the user that discovered the vulnerability should provide across the details. And you also have some additional metadata. You have information about the publish date, the date of modification, the source. And also you can find some metrics that allow you to identify the criticality of the vulnerability itself. One standard is the common vulnerability score systems. Here we have a vector that provides several informations regarding the vulnerability. You can find, for example, information about, do you need some specific privileges to exploit the vulnerability? Do you need user interaction to use the vulnerability? What is the impact at the confidentiality level, integrity level, availability level? But all of this is in general summarized in a base score. And this base score is a real value between 0 and 10 that provide general information about how critical is the vulnerability. And you can see that for this example, the score is kind of high. We have 8.8. So this vulnerability has been reported as pretty critical. And together with this information, you can find some references. For example, some vulnerabilities also have the exploit associated, so you can check the exploit. You can also find information about patches that have been released. And then, more importantly, information about the known affected software configurations. For example, this vulnerability is affecting Apache Log4j version 2.0. So in this table, you can have information about which software are affected. However, Today we're going towards the era of big data for vulnerabilities. We have many databases, and all these databases have different metadata. So according to the metadata you need, you typically go in one or the other. And more importantly, the number of CVEs reported every year is increasing. We have an increasing trend. So you can see here the report of CVEs from 1999 to 2024. We have a clear increasing trend. It's also divided by quarter in this plot. So since we are going towards the era of big data for vulnerabilities, we may benefit an automation tool that can complement human expertise, and this can be AI. So we have many CVEs reported, so even a reporting time, if we may have an automated tool that allows us to prioritize vulnerabilities, this can benefit us. And for this reason, we're going to see some AI approaches, and we're going to focus on AI approaches that leverage vulnerability descriptions. So as we've seen before, the reporter of the vulnerability provides a description. This description has many details. However, it's in an unstructured format. So we have a free format description. And as humans, we can easily identify some components of this description, like the product, the version, the vulnerable component, the vulnerability type, root cause, attack vector, impact, and many other features. However, we have an unstructured format, so according to the vulnerability, we find this component in many parts of the description. So we need to create a system that is able to understand descriptions as we do. And why not use AI and the recent solutions of language models for that? So what we are going to see today is some use cases of AI-enabled vulnerability analysis. So we have an AI model that should take the description in input and should be able to arrive to a certain task. Today in AI, we have this new set of natural language processing techniques. These are techniques that are able to represent our textual representation with a vector of numbers so that models like machine learning models can act upon and can arrive to perform certain tasks. So thanks to NLP techniques, we can now know how to convert descriptions into a vector of numbers, and we can focus on the AI model component. So I guess most of you already heard about deep learning. Deep learning is a set of machine learning solutions that focuses on using a neural network as a function approximator. But what does it mean function? The function is depending on the task that we want to achieve. So in deep learning, we have these neural networks composed by a set of neurons connected by weights. And these weights are computed in a way to start from an input set of data and arrive to a certain output with a certain degree of accuracy. And these models are typically trained, which means the weights are computed, are trained in a way to arrive to the task with the degree of accuracy that is desired that we can achieve. And they're typically trained on a large volume of data. And for example, in this task, it would be a large database of vulnerability descriptions. So if we combine the two, is where most of the language models today rely. They are in the intersection between deep learning and natural language processing. These are typical neural networks that are able to start with a representation of the description and going towards a new representation of the description, a continuous representation, typically called embedding, that is able to arrive to different tasks with high level of accuracy, typically. So the advantage of language models is that they are able to generalize across many tasks. They learn patterns typically from diverse test tasks, and they are easy to adapt. And what they do is to create this embedding, which are a semantic space projection of the textual descriptions in our case. So here we can see the embeddings of one language model, SecureBERT, taking approximately 1,000 samples of vulnerability descriptions. So each of the description become a point in this space. All the points that you can see are different descriptions according to how they are understood by the language model. And since the semantic space where language models typically project textual representation is like dimensional, for example, for this model was 768 dimensional, we can reduce the space with some techniques of dimensionality reduction. This is TSNE, one of the possible techniques, so that we can see this projection in 2 dimensions and so that humans can actually see how the language model is understanding the vulnerabilities. But here the plot is still a little bit vague. We only have gray points. So maybe we can ask a human to characterize, according to some feature, the vulnerability. For example, we can color them based on the outcome of each possible vulnerability. So you can see here some labels. For example, we have in different colors vulnerabilities according to whether they allow discovery, reconnaissance, collection, exfiltration, privilege escalation, many possible outcomes for which you can exploit the vulnerability. And however, we still see some, let's say, not clear structure according to these labels. So the language model that we used was not fully separating points according to the outcome, once reduce the dimensionality of these dimensions. And the cool part of language models is that they are easy to fine-tune. So this language model can be easily fine-tuned on new tasks, such that they can achieve strong performance on new tasks with just a small new set of data. And this is what we're going to see mainly today. So as you can see here, we have a new representation of description in the continuous semantic space, which cluster better the vulnerabilities according to their outcome. And we're going to see now how we can achieve this. So first of all, why fine-tuning language model? The idea is that language models are typically trained on large amount of data. They require large training time. These are typically very large models to achieve strong performance on several tasks. So what we want to do is to adapt them to domain-specific tasks and data sets with just few data samples, because we cannot retrain a language model for each possible task. So this is where fine-tune came to help us. Fine-tuning means taking some of the layers of the language model and just changing the weights of some of the layers in order to achieve stronger performance. So we have the vector representation of the description in input. We have the several layers. And we want to adapt the weights to achieve with better performance several tasks. And today there are many approaches. One of the simplest one is just to fine-tune some layers. So we can freeze some of the initial layers typically, and unfreeze the last n layers, and just fine-tune the weights of this pre-trained language model. So update the weights with a new training process to achieve stronger performance on new tasks. This is one of the simpler approaches. Another approach is to add some task-specific layer. So the idea is that we froze all the language model that we have, all the layers, and we add a new layer that is going to perform our new task. This is going to be called head, and we're going to train only this layer. Another new solution that is arising is to use adapters. These are specific lightweight models that you can put inside layers and that can be used to fine-tune some specific components, a more advanced technique. And as we saw before, vulnerabilities are reported in some databases, such as National Vulnerability Database. But also for language models, we have some repositories. Here you can see a repository, which is also proposing a library. It's Hugging Face. Hugging Face is one of the standard repositories today. You can find here language models according to several aspects, according to tasks, libraries, datasets, languages, licenses. And one of the main ones can be the task. So you can easily find some language models according to whether they do text classification or they are trained for translation, summarization, and many possible tasks. And you can also write some query to find some specific language models. For example, here we were looking for fine-tuned language models on cybersecurity tasks. And for example, you can find SecureBERT. This is the language model we saw before in the example. And the cool part of Hugging Face is that they also provide a library. They provide some reference code that you can easily copy and paste and adapt to what you need, so that you can easily use this language model, fine-tune it as well with the Hugging Face API. And you can also find here some versions already fine-tuned of each language model. So you find the fine-tuned versions, some adapters versions. And so Hugging Face can be a reference to find these language models, to fine-tune them. And we're going to see now some use cases. So one of the use cases we're going to see now is actually what we've seen before in the plot. try to create an AI, which is going to be a language model, that predicts the outcomes of a vulnerability based on the description. This can allow us to identify outcomes that can be achieved by attackers, and also can allow us to prioritize vulnerabilities at reporting time. Since a language model can process the description at reporting time, can already provide us information about the outcomes. So this is the first task we're going to see. This is a classification task. We want to train a model that predicts some classes given the input representation. And in our cases, the classes or labels are the outcomes of the vulnerability. We have a multi-label classification task because each vulnerability can have multiple outcomes. So we can have a vulnerability that allows privilege escalation, as well as denial of service, for example. We took as a reference set of classes the Mitre attack tactics, which is a set of high-level objectives for attackers. And we took a subset of them as classes for the outcome classification. And after the fine-tuning for outcome classification, we arrived to a language model that understands vulnerabilities in the same way we've seen before in the plot on the right. We used as fine-tuning technique the addition of a task-specific layer. So it was the approach number 2 of the previous slide. And this is the pipeline that shows how we train this model, how we fine-tune this model. So we created a dataset of vulnerability descriptions that we scraped from the National Vulnerability Database. And we labeled them manually as humans. So in the text as humans, we can understand by some specific textual components what is the outcome of the vulnerability. For example, you can see here that in this description, due to incorrect buffer management, a remote client can cause a buffer overflow that can allow to execute some specific code. So we labeled with execution. In the next one, we saw a specific string, enable escalation of privilege. So we labeled it with privilege escalation. The third one is a case where we have 2 labels. So we have a multi-label case. So we created a dataset, manually labeling all these entries. And we split this dataset into training set, validation set, and test set. So this is a typical approach in AI, where you split the data in several parts so that you can better assess the generalization capabilities of the model. The dataset size was pretty small. As we said, for fine-tuning language models, we don't need a lot of data. We can also have a small set of data and achieve high performance. We're going to see if actually this is possible in our case. So our dataset size was composed by approximately 1,000 samples. And we did 20 training runs, which means that for 20 times, we split the dataset into training, validation, and test set in different proportions. And the training set is used to train the model, so to fine-tune the layers. The validation set is used to apply a technique which is called early stopping. It allows us to stop the training in the moment where we have the best generalization capabilities according to our experimental setup. And then we reported some performances on a test set. The test set is a separated set of data that the model didn't see during training. So we can assess the performance of the model in this specific set of data, which is 20% of our data set, and see the performance, which will be more unbiased. We reported some scores here, typical of classification tasks. You can see here the mean value and some confidence intervals to understand how much it ranges for 2 metrics, the F1 score and a loss value. We want to try to maximize as much as we can the F1 score and minimize as much as we can this loss value. And you can see here that we fine-tuned several language models. Some of them are specific versions of BERT. We also tried to fine-tune GPT-2, but we didn't achieve good scores. Probably our dataset was not big enough or our experimental setup, but we achieved way higher scores for BERT-based models. So among the BERT-based models, you can see here some models which are generic, such as BERT, Roberta, DistilBERT. These are trained on different kinds of data of different domains. And some which are cybersecurity specific, such as SecureBERT, which was the outperformer in this case, and we used as a final model to predict outcomes. So you can see here an F1 score of 76%. Subsequently, we can see now another use case, which is actually the use case of my PhD project, cyber attack path prediction. The question is, can AI anticipate the most critical vulnerability paths inside a network so that we can highlight some risk areas in the network and optimize potentially the allocation of some defense strategies? We're going to see this at a higher level. We're going to see how, again, we use language models for this. So to achieve this task, we use some simulation environments to train our AI, because AI systems require a lot of iterations, especially when it comes to reinforcement learning agent, which is the solution we used to achieve strong performance. So you create a digital twin of the real world, a simulation, you train the AI on that, and then you hope that the patterns that it learned can be deployed on the real world. And CyberBattle is a simulation environment that allows to achieve this scope. It simulates a network with vulnerabilities, and we can train AI attackers, or in general models that find vulnerability paths on top. So we have a graph. This is our general environment with some vulnerabilities that we can represent based on their description. Again, we can use a language model to take this description in input and represent and take each of the description, process it by the language model, and represent every vulnerability by a vector. This vector is the understanding of the language model, the embedding for each description. And we now have a graph of vectors that we can easily adapt and give an input to an agent that should learn to prioritize vulnerabilities. And in particular, in our case, the action of the agent, we're selecting a source node, a target node, and a vulnerability. But the agent should find them in a sequential way. So it should find action source node, target node, vulnerability, and then the next source node, target node, vulnerability, and so on, and find the most critical sequences. So this is our full pipeline, where again we use language models. We didn't fine-tune the language models here. We just use them pre-trained as they are to generate a vulnerability embedding, and then another AI model was attached on top. Here there are some results of the reinforcement learning agent. During the training steps, it managed to learn to maximize some metrics such as the average own nodes percentage, average discovered nodes percentage in the simulated networks, discovered credentials percentage. And once the training is terminated, we can easily use this agent to generate some logs on new networks. So it can be used to generate new logs, which are source node, target node, vulnerability sequences, and can help system administrators to find critical vulnerability paths. So this is a high-level view of what we did. In general, there could be many other use cases. You can easily find surveys for that. This is an example of a survey. CyberBench, a multitask benchmark for evaluating large language models in cybersecurity. And they characterized language models based on different tasks, such as named entity recognition, summarization, multiple choices answering, text classification. And you can easily reference the surveys to understand which language models for which task is more suited. So this can be a cool way to understand which language models to use and to avoid exploring them all. So to summarize, we are now going towards the era of big data for vulnerabilities. We may benefit AI for scaling this new era of big data. We have growing vulnerability data, metadata from diverse sources. What we can use, for example, as we've seen today as a use case, is the unstructured descriptions. We can use language models to create meaningful embeddings representing these descriptions, and we can fine-tune them to be able to have higher performance on different new tasks. We saw some use cases, vulnerability outcome classification, where we achieved a 76% F1 score on a separate set of data, and RL agents in attack simulation, where we managed to arrive to create an agent that is able to control large percentages, in our case, approximately 69% of nodes in new unseen networks. So this is our summary, and thanks for listening.
Yes, we can applaud you. Yes, very successful speech, and probably we have some questions. The first question is the more difficult to do. Who starts? Yes, Mister.
Hello, thank you for the presentation. It was very interesting. Regarding the agent, when you want to deploy it on a network to see the vulnerabilities, how is it working? Like, is it an Nmap-like thing that is going to scan everything to look for vulnerabilities and so on? How do you deploy it?
Okay, so come back to this slide. So a typical pipeline that we suggested in our research to use is to basically create a digital twin of the real network or the emulated network. And this digital twin can be created by doing a scanning, as you propose with Nmap or other tools such as OpenVAS. So you know the vulnerabilities of each node. Subsequently, you create this digital twin. You can also embed some other information in the feature vector of each node, such as firewall rules, such as information about whether each node has some services, if the ports are open. And based on this graph representation, you can then select a number of episodes. So in reinforcement learning agent, you have this episodes concept, which are basically set of iterations, basically trajectories that you can generate. In our case, will be logs. You can select a number of episodes on which you can apply your RL agent. And then you can do a mean and a standard deviation of scores. You can find a way to use the logs. So there are many potential ways to use the logs as well. Like you can apply some specific techniques for finding the most frequently target nodes, the most frequently target vulnerabilities, so you can choose them for the prioritization of defense strategies. So this is a possible pipeline.
Thank you.